All right, now we're going to be looking at absolute value equations and inequalities, starting with an introduction and then working through a few examples. So for our introduction, I want to remind you of what the definition of absolute value is. In its simplest sense, the absolute value function turns negative numbers positive and keeps positive numbers positive. Okay, so it strips away negative signs. And in a little more formal mathematical sense, it has two pieces. It's called a piecewise function. And so the absolute value of x is equal to just x itself if x started out as being positive or 0. And separately, the absolute value of x is equal to negative x is if x started out as being negative. And a lot of people are often confused about that negative sign right there. They think, why is there a negative symbol there if the absolute value is supposed to make things positive? And what that does, it actually, if we have a negative to start out, if x is less than 0 to start out, then this negative sign right here will actually turn the negative x into a positive value. Okay, the negative value of x will become positive. A negative times a negative is a positive. Okay, so that's why that's there right there. We'll do a couple examples, the absolute value of 6 and the absolute value of negative 3. Okay, so the absolute value of 6 already is positive, and so the absolute value doesn't do anything to change it. And we could plot that right here. Okay, that's the absolute value of 6 right there. The absolute value of negative 3, the absolute value bars will strip away that negative, and we will end up with a positive 3. Okay, and we can plot that guy right here. The reason I'm showing you these on a number line is to think about what absolute value actually means. You can think of it as meaning distance from 0. So the absolute value of 6 is 6 because that point is 6 away from 0. And the absolute value of negative 3 is just 3 because that point is 3 units away from 0. You never talk about negative distance. You would never say you were 3 miles or negative 3 miles away from something. You would just say you were 3 miles away from that thing. Let's solve a couple equations. We will solve these exactly the way we solve regular equations with one important difference, but we can't do that different step until we actually get down to the absolute value bars. So we have a little bit of work to do first. For these equations, I'm going to show you a little bit less of my work on the screen just because in the interest of time, I'm trying to keep us moving forward a little bit here. So I'm going to add 3 to both sides and then divide both sides by 2. And I've gotten the absolute value of x is equal to 8. And here's what I like to do for these guys. I like to start a double pathway. Once we've pared everything down to just the absolute value bars, we can start a double pathway. And the first pathway is, what if the absolute value bars didn't do anything? What if x was positive to begin with? Okay, x is just 8. The other possibility is, what if the absolute value bars stripped away a negative sign? Okay, and then we can solve for x and we get x is equal to a negative 8. I'm doing this a little bit different from the way textbooks do it. It's equally valid though. A lot of textbooks go straight to the negative 8. But I'd really like to think of what the absolute value bars could have done. It could have removed a negative sign associated with that x, kind of. Okay, it makes a little more intuitive sense, I think. It's a little bit less formal mathematically, but I think it makes a little bit more intuitive sense to think about what could those absolute value bars have done, and could they have removed a negative sign? Let's do this next one over on the right. We'll subtract 5 from both sides first. And we get an absolute value is equal to 2. We can't deal with the 3 until we deal with the absolute value bars. So we could have the simple scenario where the absolute value bars didn't do anything. They just kept a positive as a positive, and x is equal to 5. We could have an alternate situation where the absolute value bars could have stripped away a negative. And once we go ahead and solve, we get x is equal to 1. I think it's worthwhile on this one to just show a quick check for the x is equal to 1 solution. I'm going to plug it back in. into our original equation, and is that all going to equal 7? is the absolute value of negative 2 plus 5, is that equal to 7? It is. It checks out. Okay, so that's a good way to check. I would check the more complicated ones for sure. Okay, let's go ahead and solve another one. We're going to subtract 5 from both sides first, and then we could divide by 3. And then this is an example of where you need to pay attention. Hopefully maybe you've noticed something curious here. We have the absolute value of something equal to a negative 1, which I hope you can tell is impossible. That could never happen. Okay, and so there are no solutions to this one. If you don't notice that, if you don't pay attention, you could keep going and get a couple numbers equal to x, but they would not be valid solutions. If you plugged them back into check, they wouldn't check out. So just pay attention, and if you ever notice something like that, when you have the absolute value equal to a negative, you have no solutions. Let's go into a little bit of inequalities here. And I have two types of inequalities, what I call between or beyond inequalities. Okay, the first one is I call it a between because it has a less than symbol, and the second one's a beyond because it has a greater than symbol. Okay, so let's go ahead and simplify each of these. So this says that x could have been x is less than or equal to 3, or it could have been negative x is less than or equal to 3, which means x is greater than or equal to negative 3. Okay, remember to flip the symbol whenever we divide by a negative. Okay, we had to divide by that negative right there. So let's graph it up. X is less than or equal to 3, and x is greater than or equal to negative 3. So anywhere in between those, including the endpoints, are valid solutions. Next one is what I call a beyond or an or inequality when we have a greater than symbol. And let's follow our double pathway. X could have just been greater than 2 to begin with, or we could have had a negative x is greater than 2, which means x is less than negative 2. Again, flipping your inequality symbol. X is greater than 2, so we have something like this. X could be any number larger than 2 or any number smaller than negative 2. So hopefully you can see why that's a beyond inequality. It's outside of our two endpoints. Let's go ahead and solve one. Okay, so we have here an inequality where we could divide by 3 first. And we could start our double pathway. So we have x plus 1 is greater than or equal to 4, or a negative sign could have been removed. And let's keep following this first pathway. This means x is greater than or equal to 3. So that's one portion of our inequality. Let's divide by negative 1 on the other one. X plus 1 is less than or equal to negative 4. So x is less than or equal to negative 5. Okay, so we can go ahead and graph this guy. X is greater than or equal to 3, so we have something that looks like this. Or x is less than or equal to negative 5. So any numbers in there would work. Sometimes as a quick check, what I like to do sometimes is just plug in an extreme possibility, like negative 100. So negative 100 plus 1 is negative 99. Absolute value of that is positive 99 times 3 is definitely greater than or equal to 12. So that seems to check out. Lastly, we're going to solve a quick between inequality. We can divide both sides by 3. And then we can start our double pathway. So the first one's the simple one, where the inequality didn't change any signs. And I'll keep going with that. 4x is less than or equal to 12, which means x is less than or equal to 3. Next one is a little more complex scenario where the inequality could have stripped away a negative symbol. Let's divide by negative 1. To remove that symbol, we'll flip the sign. And let's see, subtract 2 from both sides. We get 4x is greater than or equal to negative 16. So x is greater than or equal to -4. So let's go ahead and graph that. X is less than or equal to 3. Going in this direction, less than. X is greater than or equal to -4. So that confirms that we are dealing with a between inequality. One easy way to check in here, let's plug in 0, see if 0 works. So is 3 times 4 times 0 plus 2, the absolute value of that? That's going to be 3 times 2. Yep, it is less than or equal to 42, so it does seem to check out. Looks like we did it correctly. So that's a good place to stop right there.